So once you have an idea of how the integration by parts formula is derived, it's a little complicated, but the basic idea is that we can start with an integral that is not easily antidifferentiated, and we can transform it into another form that is more easily integrable. Now, one of the most basic forms of this would be the integral of x e to the x. You can't do u substitution with this, and there's no way that we've learned so far about how to antidifferentiate the product x e to the x. But it's possible to transform that into another expression that could be more easily integrated. And if you recall our acronym, LIPIT, which stands for logarithmic, inverse trig, polynomial, exponential, and trigonometric, this is the pecking order that we're going to use to identify which function should be u. So we have an algebraic, or we have a polynomial and an exponential. So polynomial comes before exponential, and that's what we'll use for u. So we let u equal x and let the remainder be e to the x dx. Now you can see from this, first of all, that the derivative of x is simpler than x itself. It turns out to be just 1. And also that e to the x dx is easily integrated. Of course, we could find the derivative of e to the x easily, except it doesn't give us something simpler than we started out with. And on the other hand, the integral of x gives us something even more complicated than we started out with. So we're looking for something that we can find the derivative of that's simpler than its original form, and we're looking for something to be dv that will be easily integrated. We will always complete these steps with integration by parts. We're first going to find the differential of u, and that turns out to be just dx. Then v will be the integral of dv, and in this case that will simply be e to the x. So recall the formula. The integral of u dv, which would be the integral of x e to the x dx, can also be written as uv minus the integral of v du. And when we do this, we'll see that the integral of x e to the x dx can be rewritten as uv, which is x e to the x, minus the integral of v, which is e to the x, du, which is dx. And you can see that now the integral in our expression is much easier to integrate than x e to the x. And so we end up with x e to the x minus just e to the x plus c. Okay, so you try one. You want to find the integral of x over e to the x dx. And you can pause the video, and I will give you the answer in a moment and work through the problem if you need that as well. Okay, well, first this would have been rewritten as the integral of x times e to the negative x dx. And for this I end up with negative x e to the negative x minus e to the negative x plus c. And I'll step through that one if you need. Otherwise you can go on to the next video. So according to LIPIT, we're going to choose the polynomial x before the exponential e to the negative x. So u equals x, dv equals e to the negative x dx. We find the differential of u, so du is equal to dx. We find the integral of e to the negative x. And you could do u substitution on this, but you should learn that the integral of e to the negative x is just negative e to the negative x. And recall our formula. Integral of u dv, which is the integral of x times e to the negative x dx, is equal to uv minus integral v du. Now we'll put that all together. uv is x times negative e to the negative x, or negative x e to the negative x, minus the integral of e to the negative x dx. Actually, that should be minus the integral of negative e to the negative x dx. So we bring out the negative and it becomes plus integral e to the negative x dx. We end up with negative x e to the negative x minus e to the negative x plus c. And that does it.